Hello guys, and welcome once more to this new video on my YouTube channel, where we are going to be solving a Cameroon DC examination Florida Mathematics paper 2 question 10. So the question was on recursive sequence. The question reads: a sequence un is defined recursively by u0 equals to a half, un plus 1 equals to e to the un divided by un plus 2. Given that a function f is such that the interval 0 to 1 is mapped onto a set of array numbers, is defined by f of x equals e to the x divided by x plus 2. Romans 1. Find f prime of x and f double prime of x. Romans 2. Obtain the table of variation of f. Romans 3. Use mathematical induction to prove that for all n belonging to the set of natural numbers, 0 is less than or equals to un less than or equals to 1. Show that Romans 4. For all x belonging to the interval 0 to 1, the absolute value of f prime of x is less than or equals to 2/3. Romans 5. The equation f of x equals x has a unique solution. Romans 6. For all l belonging to the interval 0 to 1, the absolute value of un plus 1 minus l is less than or equals to 2/3 times the absolute value of un minus l for all n belonging to the set of natural numbers, and that in general the absolute value of un minus l is less than or equals to a half times 2/3 raised to the power n. Romans 7. Hence show that the sequence un is convergent. Let us then move into the solution of this question. So we have been told that we have our sequence un, which is defined recursively by u0 equal to a half, un plus 1 equals e to the un divided by un plus 2, and that we have a function f which is such that the interval 0 to 1 is mapped onto a set of array numbers, is defined by f of x equals e to the x divided by x plus 2. Romans 1 is asking us to find f prime of x and f double prime of x. So in order for us, let us first of all put up our function. Okay, in order for us, in the first place, let us first of all obtain f prime of x actually. In order for us to get f prime of x, we are simply going to differentiate f of x using the quotient rule, since f of x is actually a rational function. So differentiating f of x using the quotient rule, we are going to obtain f prime of x to be equal to x plus 2 times e to the x minus e to the x times 1 divided by x plus 2 squared. Factorizing e to the x in the numerator, we are going to have e to the x in the numerator times x plus 2 minus 1, from which we are going to obtain f prime of x to be equal to e to the x times x plus 1 divided by x plus 2 squared. So this is actually f prime of x. Let us then get f double prime of x. So to get f double prime of x, we are simply going to differentiate f prime of x actually. So since of course as well f prime of x is a rational function, we are still going to differentiate f prime of x using the quotient rule actually, in order for us to obtain f double prime of x. So differentiating f prime of x using the quotient rule, we are going to obtain f double prime of x to be equal to x plus 2 squared times e to the x plus 1 plus e to the x times 1 minus e to the x times x plus 1 times 2 times 1 times x plus 2 divided by x plus 2 raised to the power 4 actually. So further simplifying, we are going to obtain f double prime of x to be equal to x plus 2 times e to the x, all that times x plus 2 squared minus 2 times x plus 1 divided by x plus 2 raised to the power 4. So you can clearly see that this x plus 2 is going to remove one x plus 2 in the denominator, so that we are going to be left with f double prime of x to be equal to e to the x times x squared plus 2x plus 2 divided by x plus 2 raised to the power 3 actually. So this is actually f double prime of x. Let us then move into the Romans 2 actually of this question, that is we are asked to obtain the table of variation of f. So in order for us to obtain the table of variation of f, okay, what do we need? The first thing we need first of all to do is to study the sign of f prime of x, okay, in the interval 0 to 1. If we know, okay, the sign of f prime of x in the interval 0 to 1, we can therefore conclude the behavior of our function f of x in that interval 0 to 1 actually. Yes, so studying the sign of f prime of x actually will enable us, okay, to know the behavior, okay, of our function f of x in the interval 0 to 1 actually. Yes, so we had our derivative f prime of x to be equals to e to the x times x plus 1 divided by x plus 2 squared. We know that for every x, okay, for all x belonging to the interval 0 to 1, x plus 2 squared is always greater than 0. Also, x plus 1 is always greater than 0, and e to the x is also greater than 0, okay, in this interval 0 to 1. From which we can therefore conclude that f prime of x actually is greater than 0 in this interval. That is, f prime of x is greater than 0 in the interval 0 to 1 actually. Yes. So since we already have actually the sign of f prime of x, let us then determine let us now determine the images actually. So the image of 0 is actually f of 0, which is equal to a half, and the image of 1 is actually f of 1, which is e divided by 3. Since we already have these two things, actually we can therefore proceed by coming out with our table of variation actually. Yes, obtain our table of variation, of course, x, okay, which is belong to the interval 0 to 1, the sign of f prime of x, which is positive, and since the sign of f prime of x is positive, therefore our function f of x is going to be strictly increasing in the interval 0 to 1. And of course the images, that the image of 0 is actually a half, and the image of 1 is actually e divided by 3. This is actually therefore the table of variation of f. Let us then move to the Roman 3. The Roman 3, we are being asked to use mathematical induction to prove that for all n belonging to the set of natural numbers, 0 is less than or equals to un less than or equals to 1. So we know that u0 actually is equals to a half, and un plus 1 is equals to e to the un divided by un plus 1 actually. Yes, from which we can therefore conclude that un plus 1 is equal to f of un clearly. Yes, so let us then actually prove this using mathematical induction. The first thing, let us first of all put this statement to be p, that is, let p of n be our statement which we want to prove after. Let p of n be equals to 0 less than or equals to u of n less than or equals to 1 actually. So let us prove whether it is true for n equals 0. So for n equals 0, we get p of 0, okay, to be equals to 0 less than or equals to u0 less than or equals to 1. We know that u0 is actually what? u0 is a half. Substituting u0, that is substituting half, okay, when we see u0, we have 0 less than or equals to a half less than or equals to 1, and which is true. Therefore it is then true actually for n equals 0. Let us then assume that our statement is true for n equals k. That is, assume pk is true actually. Yes, so since we assume that pk is true, using this assumption, okay, we have actually to arrive, okay, to an we have to then to arrive, okay, to a proof that it is true for n equals k plus 1 as well. Yes, so knowing that since for all x, okay, belonging to interval 0 to 1, f of x is strictly increasing, that the f of x is strictly increasing in this interval, from our table of variation we saw it clearly. It therefore means we can write this statement, that is, we can write that f of 0 is less than or equals to f of uk less than or equals to f of 1. What is f of 0? F of 0 is a half, and f of 1 is actually e divided by 3. We therefore get this expression, that is a half less than or equals to uk plus 1 less than or equals to e divided by 3 actually. Yes, but since we know that what, we know that this interval, let's say interval a half e to the 3 is inside the interval 0 to 1, okay, it means this boundary we can therefore put in the place of half we put 0, and in the place of e divided by 3 we can still put actually 1 there. So saying that, it implies we are going to have this actually, that is 0 less than or equals to uk plus 1 less than or equals to 1, and we have clearly proven that it is true for n equals k plus 1, that is pk plus 1 is actually true. We can therefore conclude that hence for all n belonging to the set of natural numbers, 0 is less than or equals to un less than or equals to 1 by mathematical induction. Yes, actually in Romans form we are being asked to show that for all x belonging to the interval 0 to 1, the absolute value of f prime of x is less than or equals to 2/3. How can we come out with this proof? Actually, we are going to actually use the same methodology which we did when we were drawing our table of variation actually. That is what, but in this case we are going to consider f double prime of x. That is, we are going to obtain the sign of f double prime of x and from there we identify that in the interval 0 to 1, of course, and then we then identify, that is, get the behavior of f prime of x in that interval 0 to 1 actually. Yes, so that is getting the sign of f double prime of x, and from there we look at the behavior of f prime of x in the interval 0 to 1 actually. Yes, so we had our f double prime of x to be equals to e to the x times x squared plus 2x plus 2 divided by x plus 2 raised to the power 3 actually. Let us get the sign of f double prime of x. So we know that for all x, okay, belonging to the interval 0 to 1, x plus 2, okay, raised to the power 3 is always positive, that is always greater than 0. E to the x of also is also greater than 0, and x squared plus 2x plus 2 is also greater than 0 for all x in the interval 0 to 1 actually. From which we can therefore conclude that f double prime of x is actually positive actually here. So f double prime of x is actually positive, and since f double prime of x is positive, okay, in this interval, that is greater than 0 in this interval, that is for all x in the interval 0 to 1, we can therefore conclude that actually f prime of x, okay, is strictly increasing in the interval 0 to 1 actually. Yes, so saying that implies f prime of x, as I said, yes, is strictly increasing for all x in the interval 0 to 1, from which we can therefore write this statement, that is f prime of 0 is less than or equals to f prime of x less than or equals to f prime of 1 actually. What is f prime of 0? F prime of 0 is actually 1/4, and the f prime of 1 is 2e divided by 9 actually. Yes, so since the proof actually we are looking at the absolute value, we have the absolute value here, it means we are going to actually focus more on what is on the right hand side here actually. Yes, so we have to look at, you have to study, that is, we have to study this 2e divided by 9 actually. That is, what are we going to do here on the right hand side? We know that 2e, okay, divided by 9 is less than or equals to 6 divided by 9. That is, we make them have the same denominator and try to compare the numerator for us actually to come out with this 2/3. So this statement is always true, that is 2e divided by 9 is always less than or equals to 6 divided by 9 actually. Yes, because 2e is always less than 6 actually. Yes, so from which we can therefore write 1/4 is less than or equals to f prime of x, it is less than or equals to 2/3. That is, in the place of 2, okay, e divided by 9, we write simply 2/3, because 2e divided by 9 is always less than or equals to 6 divided by 9, and if you simplify 6 divided by 9, we are going to obtain 2 divided by 3 actually. From which we can therefore conclude that for all x in the interval 0 to 1, the absolute value of f prime of x is always less than or equals to 2/3 actually. Yes, so in Romans 5, okay, we are being asked to show that the equation f of x equals x has a unique solution. So in order for us to show that the equation f of x, okay, equals x has a unique solution, we have first of all to obtain a given, okay, other function. That is, let us say f of x equals x, and from there we can send x on the left hand side, that is, we get f of x minus x equals 0, from which we can let, okay, if we can let therefore p of x to be equals to this, that is f of x minus x. So how then can we proceed in order for us to show that this equation actually has a unique solution? There are two conditions which you have to take into consideration actually to come out with this proof. The first thing, we have to show that this p of x is actually strictly increasing or strictly it's either strictly increasing or strictly decreasing in the interval 0 to 1 actually. Yes, and the second thing which I have to take into consideration is that we have to show that they exist at least one value, okay, that there exists at least one value, okay, on the x-axis in the interval 0 to 1. That is the first thing. We first of all show that this p of x is actually strictly increasing or strictly decreasing actually in the interval 0 to 1, and we make sure that they exist at least one value, okay, which touches the x-axis in the interval 0 to 1 actually. So let us first of all show, let us first of all identify whether this function p of x is either strictly decreasing or strictly increasing, okay, in the it is either strictly increasing or strictly decreasing in the interval 0 to 1. To do that, we have simply to differentiate it actually, and once we differentiate, we get the sign actually of the derivative. If the sign of the derivative is positive, it means this function p of x is strictly increasing in the interval 0 to 1. If the derivative, that is p prime of x, is negative, it means this function p of x is actually decreasing in the interval 0 to 1 actually. Yes, so getting p prime of x, we get p prime of x to be equal to f prime of x, okay, minus 1. But we proved previously that f prime of x, the absolute value of f prime of x is actually less than or equals to 1, from which we can therefore conclude that this actually is less than 1. That is, the absolute value of f prime of x actually is less than or equals to 2/3, which is, of course, since 2/3 is less than 1, we can therefore write this statement here actually, from which we can therefore conclude that f prime of x is less than 1. And since f prime of x is less than 1, we can therefore conclude that this p prime of x is actually less than 0. That is, this p prime of x is negative. And since this p prime of x is negative, we can therefore conclude that our function p of x will be strictly decreasing in the interval 0 to 1 actually. Yes, since we have proved the first condition, we have then to go forward and prove the second condition, that is, they exist at least one, that is that function p of x, okay, since it is strictly decreasing, it must touch the x-axis at least once in the interval 0 to 1 actually. Yes, so to do that, we have to rely on what we call, that is, of course, p of x is strictly decreasing. Since p prime of x is less than 0, that is, p prime of x is strictly decreasing for all x, okay, belonging to the interval 0 to 1. So as I told you, we added the second condition. The second condition, we have to rely in the intermediate value theory. You see that what that is for us, okay, to show that they exist at least one value, okay, in the interval 0 to 1. That is the interval 0 to 1. That is, there exists at least one value, okay, on the x-axis in the interval 0 to 1. Okay, we have to determine the sign of p of 0, okay, and we have to determine the sign of p of 1 if the product, that is the product of p of 0 times p of 1 is negative. Therefore, they exist at least one point, okay, which touches the x-axis in the interval 0 to 1. Yes, so let us first of all obtain p of 0. We obtain, that is, p of 0 is going to be equal to f of 0 minus 0, okay, to be equal to a half minus 0, which actually gives us a half, and we can therefore conclude that p of 0 is actually greater than 0. We do the same thing for p of 1. P of 1 is simply going to be f of 1 minus 1, which is actually equal to e divided by 3 minus 1. But e divided by 3 actually is less than 1, from which we can conclude that p of 1 is less than 0. Doing the product between the two, we obtain p of 0 times p of 1 to be less than 0. And since p of 0 times p of 1 is less than 0, we can therefore conclude that they exist at least one, that is, they exist at least one value, okay, of on the x-axis, okay, in the x-axis, one value in the interval 0 to 1, okay, when this function p of x is actually decreasing. That is, once this function is going to be decreasing, it will touch the x-axis at least once in the interval 0 to 1, from which we can therefore conclude that since p of x is strictly decreasing for all x in the interval 0 to 1, and of course p of 0 times p of 1 is less than 0, we therefore conclude that p of x equals to f of x minus 1, or f of x equals to x has a unique solution in the interval 0 to 1 actually. Yes, so this Roman 5, this is the logic. I will take it back again. That is, in order for us to show that the equation f of x equals x has a unique solution, the first thing we have, first of all, to look whether this function is either strictly increasing or strictly decreasing. That is, the function p of x, which we obtain by simply sending x on the other side, is either strictly increasing or decreasing in the interval 0 to 1. And once we identify that it is strictly decreasing or strictly increasing, in this case it was strictly decreasing, since the function is p of x is strictly decreasing, we have to show that whether it, we have first of all to identify whether it touches, okay, the x-axis in the interval 0 to 1 at least once actually. And to do that, we have to rely in the intermediate value theory, that's by getting the product p0 times p1. If this product is less than 0, therefore it touches, that is, the function p of x touches the x-axis at least once in the interval 0 to 1 actually, and which was the case. That is, p of 0 times p of 1 gave us a negative sign, that is less than 0, for which we can therefore conclude that the equation f of x equals x has a unique solution. Yes, of course. Actually, let us then move actually into the Roman 6 of our question actually, where you have been asked to show that for all L belonging to the interval 0 to 1, the absolute value of un plus 1 minus L is less than or equals to the absolute value of times the absolute value of un minus L for all n belonging to the set of all natural numbers, and that in general the absolute value of un minus L, okay, is less than or equals to half times 2/3 raised to the power n actually. So let us first of all show this first sentence, that is for all L belonging to the interval 0 to 1, okay, the absolute value of un plus 1 minus L is less than or equals to 2/3 times the absolute value of un minus L actually. Yes. So the first thing, in order for us to prove this first sentence, you have to consider the proof which we had actually, that is the absolute value of f prime of x, okay, less than or equals to 2/3. So this is a crucial analysis. This is what we must use actually to prove this first part actually, because there are two proofs here. This is the first proof and the second proof actually. So this is what we are going to use actually, okay, in order for us to come out with this proof, that is this first proof actually. We know that what the absolute value of f prime of x, okay, is less than or equals to 2/3. We prove it actually. Yes. Now if we apply the mean value theorem on the left hand side, what are we going to have? We are going to have what? The absolute value of f of un minus f of L, okay, divided by un minus L less than or equals to 2/3, where of course L belongs to the interval 0 to 1, is the unique solution of f of x equals x, that is f of L equals L actually. So replacing f of L by L, by putting L, and f of un, which is actually our un plus 1, we have the absolute value of un plus 1 minus L divided by un minus L less than or equals to 2/3. So we have simply replaced, that's the value of f of un, which is actually un plus 1, and the value of f of L, which is actually L here actually. Yes. So from where we then get actually the absolute value of un plus 1 minus L to be less than or equals to 2/3 times the absolute value of un minus L for all n belonging to a set of all natural numbers, which actually was required for us to actually to prove the first part here actually. Yes. So in the second proof, where you are being asked to show that in general we have this relation, that is the absolute value of un minus L less than or equals to a half times 2/3, okay, raised to the power n, by, we are going to use mathematical induction in this case, but there are several, you can still do it another way, okay, but in this video we are going to use mathematical induction, that is we are going to prove this by mathematical induction actually. Yes. So we have first of all, okay, let our statement p of n to be actually what we want to prove actually. So let p of n be equals to be the absolute value of un minus L less than or equals to a half, okay, times 2/3 raised to the power n actually. Yes. So the first step, okay, which we have to show, okay, for the mathematical induction, we have first of all to show that it is true actually for n equals 0, and to do that we have to use the fact that since L, okay, belongs to the interval 0 to 1, it implies actually L is greater than or equals to 0, which is true, okay. Yes. From which we can therefore multiply both sides of this equation by -1, from which we get negative L is less than or equals to 0 actually. Yes. So from there we can still add half on both sides of the equation, that is adding half on both sides of the equation, we get half minus L less than or equals to a half, from which we can therefore see that what a half is actually our u0 actually. Yes. So half is our u0, and since there is a term here that is 2/3, okay, raised to the power n, and of course we are proving true for n equals 0, okay, we want to prove that it is true for n equals 0, we can clearly see that what we can clearly have this relation at the end, that is p0 equals u0, where u0 is equals to half, okay, and here we can write half times 1, okay, which is actually 2/3 raised to the power 0. Yes. So hence p0, our statement p is true for n equals 0, because p0, which is u0 minus L, is less than or equals to a half times 2/3 raised to the power 0 actually. So we have already proven true for n equals 0 actually. Yes. So we have therefore to suppose that, okay, our statement p of n is true for n equals k actually. So suppose pk, that's our statement p of n is true for n equals k, we have actually what? We have p of k, okay, which is the absolute value of uk minus L less than or equals to a half times 2/3 raised to the power k. So you assume true for this, we assume that this statement is actually true. What then are we supposed to do here? We have to multiply both sides of this equation by 2/3. Why? Because if we multiply both sides of this equation by 2/3, we are going to obtain the relation in terms of un, of course. Yes. So what are we going to do? We have to multiply 2/3, okay, on both sides of this equation. We are going to obtain 2/3 times the absolute value of uk minus L, which is less than or equals to 2/3 times a half times 2/3 raised to the power k actually. from which we can clearly see that we proved this one in the first place. That is, this relation actually was greater than or equals to the absolute value of un plus 1 minus L. But in this case, we are going to write it as 2/3, okay, that times the absolute value of uk minus L to be greater than or equals to the absolute value of uk plus 1 minus L, and which is this relation, of course, is less than 2/3 times a half, okay, times 2/3 raised to the power k. But 2/3, okay, times 2/3 raised to the power k gives us 2/3 raised to the power k plus 1 actually. Since this, that is uk, the absolute value of uk plus 1 minus L is less than 2/3 times the absolute value of uk minus L, which is less than or equals to less than or equals to a half times 2/3 raised to the power k plus 1. We can therefore write that this relation, that is the absolute value of uk plus 1 minus L, is less than or equals to a half times 2/3 raised to the power k plus 1. Yes, so writing that, we are going to obtain this. And since we are writing this, it means we have already proven true for n equals k plus 1. So our statement P of n is true for n equals k plus 1, from which we can therefore conclude that hence the absolute value of un minus L, okay, is less than or equals to a half times 2/3 raised to the power n for all n belonging to the set of all natural numbers actually. Yes, actually, let us then move actually to the Roman 7, okay, that's question Roman 7, which says hence show that a sequence un is convergent. So to show that a sequence, okay, is convergent, we have simply to show that the limit of that sequence as n tends to positive infinity, okay, give us a finite value, okay, that is a finite number actually. Yes, so using the proof that we had previously, that is the absolute value of un minus L, which is less than or equals to a half times 2/3 raised to the power n, okay, we can also say that this actually, that is the absolute value of un minus L, is greater than or equals to 0, from which we can therefore get the limit, okay, of the middle term, okay, by simply applying the squeeze or the sandwich theorem. So applying the squeeze theorem, we get the limit as n tends to positive infinity of 0 to be equal to the limit as n tends to positive infinity of a half times 1 times 2/3 raised to the power n, which is equals to 0. Since the limit of the left hand side and the limit of the right hand side gives us 0, it implies the limit of the middle term actually will also give us 0 as n tends to positive infinity actually. Yes, so since the limit as n tends to positive infinity of the absolute value of un minus L give us 0, it simply implies that the limit as n tends to positive infinity of un is equals to L. And since we know that L is unique, okay, that is L is finite, we can therefore conclude that our sequence un is actually convergent actually. Yes, so thank you very much for watching this video, and please, I would like you to share, comment, okay, subscribe to the YouTube channel, okay, so that the YouTube channel can grow. And of course, once more, don't forget to share for your friends also to benefit from the content. Thank you very much, and remain tuned for a very next interesting video. Thank you.